In this video, I'm going to go over the manipulation of various power series. So first I want to review the big four, the four that you must know for the AP exam. This first one is our infinite geometric series with an A1 of 1 and a common ratio of x. So if we write this out, this is 1 plus x squared plus x cubed and so on. The general term is x to the n. Okay, e to the x is all of them. So you could do all of these, you could derive all of these from your Taylor and Maclaurin series formulas, but these are ones that you want to memorize. So this is all, and they're all positive. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Okay, cosine is our even function, sine is our odd function. So cosine is 1, this one alternates, minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. The general term here is negative 1 to the n to make it alternate, x to the 2n to get the even powers over 2n factorial. And then sine is the odds. So sine is x, it again alternates. Okay, we still have that negative 1 to the n. But this is going to be x to the 2n plus 1 over 2n plus 1 factorial. And these can be minus 1s as well. Now we're going to take our known series and manipulate them in various ways. So e to the negative x, we're going to take the series for e to the x and substitute. So now we're going to have 1 minus x plus, will be negative x squared over 2 factorial plus negative x cubed over 3 factorial, and so on, which is going to be 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, and so on. So my general term is going to be negative x to the n over n factorial. Okay, we'll do the same thing with 2. So my general term is just going to be 2x to the n over n factorial. Okay, we're going to substitute a cosine into or 3x into our cosine, which is our evens. And then substitute into the general equation. Okay. For this next one, I'm going to build this series, starting with cosine. Okay, so we're going to write cosine. Then I'm going to subtract 1. Which will leave on this side negative x squared over 2 factorial, x to the 4th over 4 factorial, x to the 6th over 6 factorial. Since we lost a term, I'll go ahead and add the next one because we need 4. And then divide everything by x. So you get negative x over 2 factorial x cubed over 4 factorial, x to the 5th over 6 factorial, x to the 7th over 8 factorial. Then we'll come up with our general term. We are alternating. And I'm going to try to get it so that I can plug in a 1 to get this term. So we're going to have negative 1 to the n. So if I plugged in 1, we'd get negative. It's going to be x to an odd power, so 2n minus 1 if I want to plug in 1 for that. And then this is 1 higher than that, so we get 2n factorial. Okay, for the next one, I'm going to go ahead and write cosine out again. Okay, then I'm going to multiply by x squared. Which is going to make all of these powers over here go up by 2. For my general term, we're still alternating. And I'm going to do it so I can plug in a 1 to get this. So if I plugged in 1, this would be negative, so I'll go ahead and do a plus 1. My power is going to be x to the 2n, and then my denominator is going to be 2n minus 2 factorial, because whatever the factorial is 2 less than whatever this power is. Next, we're going to form series by more multiplication, but there's different pieces here we have to work out. So this first one, I'm going to multiply x plus 1 times cosine. Okay, which is going to be x plus 1 times the series for cosine, 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, and so on. Okay, which means we need to essentially FOIL in a way, basically distribute. So I'm going to multiply all of these by x. And then I'm going to multiply them all by 1. So now these are definitely not in the correct order, but we'll fix that in a second. Okay, what we want for this is the 3 non-zero terms. So my non-zero terms are going to be 1. I've got a linear term, and I have a squared term. So that would be 3 non-zero terms. For this next one, it's going to be the same kind of thing, but we're actually multiplying an infinite series times another infinite series. So how I'm going to organize that is with a chart. So in my chart, and this is, you can organize it how you want to, this is just how I find helpful. I'm going to put e to the x up here, and I'm not sure how many terms I need, so I'm just going to give myself some wiggle room here. 2 factorial, x cubed over 3 factorial, but I'm going to go ahead and write it as 6 to help my math. And then x to the 4th over 4 factorial, which is 24. On this side, I'm going to write my terms for sine of x. So that's going to be a positive x, a negative x cubed over 3 factorial, and a positive x to the 5th over 5 factorial, which is 120. Okay, and then you're simply just going to multiply. So I can multiply all of these by x. Okay, I'll multiply all of these by 1. That's easy to do. And I'm not going to need this whole chart filled out. So I'm going to go to maybe about degree 5 and see where we go. So if I multiply by x here, we get negative x to the 4th over 6, x to the 6th over 120. If I multiply these two together, I'm going to get a negative. And then x squared times x to the cubed is x to the 5th, and then 6 times 2 is 12. This would give me a 6th degree polynomial, so if I need to go that far, I can fill that in, but we're probably good without it. Okay, and then I'm just going to look for my degrees. So I have a degree 1, so x. I have 1 degree 2. I have 2 degree 3s. So I've got an x cubed over 2 minus x cubed over 6. Okay, I've got to do 2 degree 4s. But unfortunately, it would be nice if we could stop there. But we're going to have x to the 4th over 6 minus x to the 4th over 6. So those terms end up canceling each other out. And then my last ones are going to be these 3. Okay, so I'm going to have x to the 5th over 24 minus x to the 5th over 12 plus x to the 5th over 120. Okay, so we're going to go ahead and combine these, because right now you can't have multiple x to the 5th, so we need to condense that. So I'm going to have x plus x squared. This would be 3x squared over 6 minus x over 6 is 2x squared over 6, or x cubed over 3. That one goes away. And then I could get a common denominator. I'm going to cheat a little bit and just say 1 over 24 minus 1 over 12 plus 1 over 120 x to the 5th. Okay, all of these ones are infinite geometric. Okay, so we're looking for a1 over 1 minus r. Okay, so I can expand it out because my a1 here is 1, my r is 3x. So we have 1 plus 3x plus 9x squared, and so on. This one, my a1 is 2, my r is a negative 3x. So I can write this out as 2 minus 6x plus 18x squared. This one, my a1 is 2, and my r is a positive x cubed. So this is going to be 2 plus x cubed, 2x cubed, plus 2x to the 6, because we add the exponents. This one, unfortunately, is not in the right format. This 2 needs to be a 1. So I can factor that out and make this 1/2 over 1 minus x over 2. So my a1 is 1/2, and then my common ratio is x over 2. So we'll have x over 4 plus x squared over 8, and so on. Okay, now we're kind of going backwards. When presented with the series, trying to come up with the function. So here, we've seen a lot of cases where I'm able to change the powers by multiplying or dividing by something. So if I look at the factorials, we have odd factorials. So odd is equal to sine. Okay, so sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So I want to say, how can I get from here to here? Well, the denominators are fine, but the numerators are off by a factor of 2. So what I can do is multiply it by x squared, and then I get x cubed minus x to the 5th over 3 factorial, and so on. Okay, this next one is infinite geometric. So this is a1 is x. My r is also x. So this is x over 1 minus x. So we're looking at what it matches which function. So looking at it, they're all positive, and we have all the factorials, and we sort of have all the powers. So it's not going to be sine or cosine, so I can eliminate those ones, which leaves me with e to the x. So what I'm going to do is write out e to the x and do some manipulations to try to arrive at this. So e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial, x to the fourth over 4 factorial, and so on. Okay, so if I'm trying to match this, we sort of have the 2, 3, 4, which means I want to get rid of those. So that leaves me with x squared over 2 factorial plus x to the third over 3 factorial, x to the fourth over 4 factorial. To arrive at these, I want that 2 to become a 4, 3 to become 5, 4 to become 6. So I'm going to multiply them by x squared. But just like any equation, if I do something to one side, I need to do it to the other side. So I'll multiply this by x squared, I'll multiply this by x squared, and I'll multiply this by x squared. Okay, it's in a slightly different order, but it is D. Okay, so this is from the 2015 test. We have the general term for our series, and then it's expanded out a few terms here. And it converges for absolute value of x is less than r, where r is the radius of convergence. So first we're going to find the radius. We'll use the ratio test as it says. Okay, so I'm going to take my general term and add 1 to it. So that's going to be negative 3 to the n, x to the n plus 1 over n plus 1 over negative 3 to the n minus 1, x to the n over n. Okay, the alternating piece, which sometimes I don't put in, but I did for this time, goes away. Apologies, I misspoke. We need the negative 3 to the n's because it will make it alternating, but it is also a part of the exponential function. So I'm going to break it down. I'm going to rewrite this negative 3 to the n as negative 1 to the n times 3 to the n, x to the n times x over n plus 1. Okay, and then we'll multiply by the reciprocal here. So I'm going to have n. I'm going to have negative 3 to the, so I'll break this down. So negative 1 to the n and 3 to the n minus 1, which is going to be the same as, do one more thing before I cross stuff off, and I could cross stuff off already, but I'm going to rewrite this one as n negative 1 to the n, 3 to the n times 3 to the negative 1. So that's going to be interesting. Okay, the negative 1's go away, the 3 to the n's go away, the x to the n that I forgot to write goes away. Okay. This x to the n needed to be here, but it cancels. This cancels with this one. Okay, so what this leaves me with is a lone x that I can pull out with the absolute values. Okay, on the top we have an n, but we also have a 3 to the negative 1 in the denominator. So this is going to be 3n over n plus 1. So we get this times 3. We need that to be less than 1. So we want negative 1 to be less than x. 3x is less than 1. So negative 1/3 is less than x is less than 1/3. So our radius, which is what we're asked to find here, is 1/3. The second part says write the first 4 terms of the non-zero terms for the Maclaurin series f prime expressed as a rational function. Okay, so if I need to find the derivative of 4 terms, I need 4 terms. So I copied down the 3 that were provided and then generated the next one. Then we're just going to do a power rule here. So we're going to have 1. If I multiply this by 2, we're going to have 3x. If I multiply this by 3, we get 27x squared. And if I multiply the 4, that cancels, and we get minus, 3 times 3 is 9. Looking at my notes. 4 times 4, 4 times 1/4 cancels, 27x cubed, and so on. Then it says to write this as a rational function, which is kind of your hint as this is going to be infinite geometric. So this is going to equal a1, which is 1, over 1 minus r, which was a negative 3x. And then the last part of this question says write the first four non-zero terms of e to the x. So you get points for knowing e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial. Okay, then we're going to use it to rate the third degree Taylor polynomial for e to the x f of x. So I'm going to multiply these together, and again I'm going to make a chart. Okay, so in my chart I have the first 3 terms of e to the x up here, the first 3 terms of my f of x here, and then we'll just multiply. Again, I'm not going to have to multiply everything, but we'll do the easy ones and see where we're at. So multiply this all by 1, that's easy. Multiply all these by x, so x squared, x cubed over 2. And we've got some degree 3, so let's go ahead and do degree 3 x cubed there if I multiply x squared times x. So I'm looking for 4 terms. If I need to get more, I will. Okay, but g of x, which is e to the x f of x, I have an x here, and then we've got x squared minus 3 halves x squared. So that's going to be my second term. Sorry, I guess I failed to mention that. We just want a third degree, which is why I needed to stop there. So then I've got 3x cubed minus 3 halves x cubed plus x cubed over 2. Okay, we can't write it like this. A lot of times we can leave stuff unsimplified, but we need to condense the coefficients. So x, I've got, this will be negative 1/2 x squared when we condense that. Getting a common denominator, or adding these two, I'm going to have a negative 3 halves plus that is going to be a negative 1. All right, and our last problem is the 2019 series question. So first we're going to write the third degree Taylor polynomial about 0. Okay, so I've written my template for the Taylor series. We're given a chart that gives me the second, third, and fourth derivatives, but we also need the first and second. We're also provided the graph and the tangent line, and we're all about 0 here. So my f of 0 is just the function value at 0, which is 3. The derivative we can get from the slope. The slope of that tangent line is negative 2, so my first derivative is negative 2. And then these two we're just going to get from the chart. Okay, so that's all there is to it. Okay, this is the second one. The 2016 and the 2019 had virtually the same kind of question. First, we get points for the 3 non-zero for e to the x. E to the x is 1 plus x squared over 2 factorial. And they just want 3. So there you go. Next, we're going to multiply. So I'm going to use my chart. I'm only looking for a degree 2. So I put my first 3 terms of e to the x here. And then the 3 terms up to degree 2, because going pi is not going to matter. And then do my multiplication. So multiply all these by 3. And I only need to get to degree 2. Okay, so my last one is going to be x times negative 2x. Okay, and then we'll pull those out of the chart. So the 3rd degree Taylor polynomial here for e to the x f of x, or 2nd degree, is, we got a 3. I have 3x plus 2x, so that will be x. 3 halves x plus 3 halves x will be 6 halves x, or 3x, minus 2x plus x squared. Okay, part C, we want to integrate f of x. Okay, so, and then, so we're going to use, so h of x is the integral from 0 to x of f of t dt. We're going to use the Taylor polynomial we found in part A to find an approximation for h of 1. So h of 1 is going to be the integral from 0 to 1 of f of t. I'll go ahead and simplify that one. That would be negative 23x cubed, well, t cubed, over 6 times 2 would be 12. Okay, so we'll integrate here. Okay, I'm going to add 1 to the power and divide by that power. So this will be just t cubed over 2. Add 1 to the power, divide by that power. I'm going to have negative 23t to the 4th over 48. We'll evaluate this from 0 to 1. So if I plug in 1, we're going to get 3 minus 1 plus 1/2 minus 23 over 48. If I plug in 0, all of those go to 0. So we're just going to leave it just like that. Okay, final question. Got a lot of words to it. It is known that the Maclaurin series converges for h of x for all real values. It is also known that the individual terms for the series h of 1 alternate in sign and decrease in absolute value to 0. Use the alternating series error bound to show the approximation found in C differs by h of 1 by at most 0.45. Okay, well this is the alternating series error bound, which means we want the next term in this series. Okay, so first I need to find the 5th term because we don't have the 5th term. Okay, that's going to be the integral from 0 to 1. I need to generate the next term using the fact that my 4th derivative is 54. Okay, so we'll integrate this. So I'm going to add 1 to the power and divide by that power and evaluate it from 0 to 1. So that's going to be 54 over 5 times 24. Okay, we can do some simplifying here. When we do that, we end up with 9 over 20, which is equal to 4/5. So my error is less than 9 over 20, which is equal to 0.45. Okay, and that's manipulation of series.